Hey, and welcome back to Alchemist Camp, where we learn Elixir by building things. And today, I'm going over the answer to challenge number 9, which was not really Elixir specific, it was just to make a state machine to model a game that you know. I chose the game of concentration, or memory. So as you may recall from childhood, there's an old game, originally a card game, where both players lay out all the cards on the ground, and then they take turns flipping up two cards, one at a time. And if the two cards they flipped up match, then they get to keep them. If not, they flip them back over, and it's the other player's turn to flip up a card and then flip up another card and see if they match. So it's essentially a game of luck and memory to remember where the cards you've seen before are, and you can match them if you see them again. This is pretty widely known, which is why I picked it, and we'll go into a preview of a markdown file I made of it. So the states in this game are initial, which is before the cards have been laid out on the floor or anything. Then after that's done, there's a state where it's player one's turn with no cards flipped up. They flip up a card, then it's player one's turn with one card flipped up. They do it again, then they have two cards flipped up, and then they check to see if the cards match or not, and either they have a match or they don't. If they have a match, they take the two cards, and then it's their turn again with no cards flipped up. If they don't have a match, then it's player two's turn, and their states are the same. And then at the end, when there are no cards left, that's a state, and then when the game is over, that's a state. The actions are setting up the game, flipping up a card, comparing the two cards that you've already flipped up, flipping the cards back down if they don't match, taking the cards if they do match, and counting the score at the end of the game. This is a table with all the valid transitions between all the states. If something's not listed, that's because it's not a legal transition in the game of memory. On the left side, you can see a tuple where the first element is the initial state and the second element is an action. And then on the right side is the state that that action can transition the state into. And sometimes it's more than one. For example, when a player compares two cards, they might have a match or they might not have a match. So in that case, I just listed both of the possible transitions together. So I'll go through them quickly. At the beginning, you can only set up the game. Then after the game is set up, it's player one's turn and no cards are up. Then player one can flip a card, and then player one has one card flipped up. From that state, the only legal thing to do is player one to flip a card. Then they have two cards flipped up. Then either player one has a match or not. And if player one has a match, then it's player one's turn with no cards flipped up, or possibly there are no cards left. And if player one doesn't have a match, then it's player two's card with no cards flipped up. Player two's actions are just a mirror of player one's. It is not lined up right. Much better. Player two's actions are just a mirror of player one. Then at the end, when there are no cards left, the only legal action is count the score, which transitions into the game over state. Then from the game over state, players can play again. You may notice, unlike the tic-tac-toe game that we did last time, there are separate states here for whether if it's player one or player two. And from this you can kind of see a weakness of state machines, and that is, imagine if you had a four-player game like the card game Hearts. Well, then all of a sudden you'd have even more states, and if there are scores that you also want to model that get kept track of during the game, then any state machine is just going to have this combinatorial explosion of possible states. And that's why state machines are best used for a smaller number of states and their transitions that absolutely cannot be gotten wrong and that you want to be able to reason about easily. For example, whether if a credit card has been billed or not, or whether if a customer contract is still ongoing or not. And I've got a couple of links for you if you want to learn more about this kind of thing. The first is Wikipedia. It's a finite state machines article, which you can Google pretty easily. And the second is OpenCourseWare, which is basically full free university courses on the internet. Has a course on automata, which starts off with state machines. In fact, this is, I believe, a diagram of one right here. And then it goes on and teaches regular expressions and context-free grammars, and then eventually a full-blown Turing machine. And if you didn't come from a CS background, I actually think this course is the most useful one in an undergraduate CS curriculum in terms of being able to apply it to your job later. Well, except maybe data structures and algorithms, especially since that pops up in interviews so much. But with that one exception, I think automata is the one to go for. So I highly recommend it if you're into this stuff. Also, there's a finite state machine built into the Gen server in Elixir called Gen FSM. But there's another repo here, which is by a fairly well-known Elixirist, that is just a pure state machine that doesn't have the complexity of OTP and a Gen server and all that. It's definitely worth checking out as well. And finally, the answer to the second part of the question is how the tic-tac-toe state machine could have been structured to be easier. My solution is actually just not to use a state machine for tic-tac-toe. Tic-tac-toe doesn't really need it. You can actually find whole solutions of tic-tac-toe that are fewer lines of code than our state machine module is. But state machines are very good to know how to use, and they can be used for a lot of games other than just tic-tac-toe. And in future videos, we'll be changing out the interface of the tic-tac-toe game very painlessly. So definitely stay tuned for that. Click subscribe, click the bell, and I'll see you tomorrow.